Hello everyone, this is Professor Iris Miano coming at you with a day 14 lecture concerning more logarithmic and exponential goodness. We're going to solve some logarithmic and exponential equations, more advanced style ones compared to the last lecture, and then we're going to get elbow deep into some application problems concerning financial models, Newton's law of cooling, exponential growth and decay, and there's also a logistic model that's going to wrap things up. A little bit of population modeling at the end there. So lots to cover. Let's go ahead and dive right in with the 4.6 business, which is basically a review, but we're going to be entertaining some more complex logarithmic and exponential equations in our process of finding the solutions. So the textbook went ahead and reminded us of a few of the properties of exponential equations and logarithmic equations, so note those of course, plus all of the other ones that we learned as well as we solve the following equations. So the first one, you'll notice that's number 6 out of the textbook. We're going to solve a logarithmic equation. If there's any irrational solution, we're going to give it in its exact form and also a decimal or 2 3 decimal places. Okay, so here we go. Let's go ahead and look at this first equation and recognize that we have a log with no explicitly shown base. So we know that that's supposed to be representing log base 10, right? So it would behoove us, since the x's that we're trying to solve for is in the argument of the log, to convert it into its exponential counterpart, which is going to be the base is the base, right? So the base of the common log is 10. The log is equal to the exponent, which is 1. And the exponential expression is equal to the argument, which in this case is x plus 6. We must then, therefore, simply subtract 6 from both sides. 10 to the first power is just a 10, and we can just go ahead and say x therefore equals 4. Of course, you want to be taking into account that arguments for logs have to be positive, so certainly whatever you get as your calculated value for x has to be greater than -6, right? Like, we have to keep that in mind as we go, and certainly that will become relevant in subsequent examples that we're about to entertain, in which we will calculate some solutions that are technically extraneous. So let's keep our eyes peeled for that. Moving on to example 12, though, you'll notice that we have 2 logarithms set equal to each other. One of them has a scalar multiple out in front, this -2. So the way that I would start off this process is to let this -2 kind of come upstairs and become an exponent on the x. That way we have 2 logarithms set equal to each other with no other factors. They happen to have the same base. So once that is in play, we can just cancel out the logarithms on both sides. So it'll look like this. Okay, once you have this, again, like I said, cancel, cancel. Now you can just set the arguments equal to each other. X to the -2 equals 9. And then what shall we do with that? Well, this negative exponent right here is, in needing to be evaluated, puts that x squared in the denominator space. Now, if we want to bring that x squared up to a numerator space, it's kind of like we would have to flip over both sides, which we can do. We can have this 9 be over a 1. I'm going to go ahead and continue right here with it and go, okay, so it's 1 over x squared is equal to 9 over 1. So therefore, x squared should equal 1/9. Luckily, both 1 and 9 are perfect square numbers, so we can rewrite them as something squared, right? Yes, there we go. And taking the square root of both sides, what does that look like? In order to get the x all the way by itself. technically I can understand how you'd be like, oh, hey, wait a second. Now I know these square root and square root will cancel each other out, and that's all well and good. But I gotta put the plus minus here, right? Technically, algebraically, yes, you would do that, but recognize that this x value that we're about to calculate is in an argument of a logarithm, so it has to be positive. So in that regard, we would actually not need to take the negative counterpart of the square root. We would just take the principal square root and leave it at that. So therefore, x will equal simply just one single factor, 1/3. Let me put a little note here, since x has to be greater than 0, because that is the argument of one of the logarithms. Okay? Okay, cool. Moving on to number 16. Notice that we have a difference of logarithms on one side of an equation and then just a constant of 2 on the other side. And one of the logarithms has a scalar multiple of 2. Right off the bat, I'm like, let's go ahead and put that up to be an exponent in the argument. And that will look like the following. Log base 3. The x plus 4 squared minus log base 3 of 9 equals 2. Now we have two logs that are, one is subtracted from the other, and they have the same base. So we can use what we know about differences outside of the same base logs, make for quotients inside the single log of the same base, of that collective base, rather. Okay. So we can, at this point, convert this equation into its exponential counterpart, its exponential version, which I think would be good to do. So we have the base is the base, right? The base of the log is the base of the exponential version. The log is always equal to the exponent, and the exponential expression is always equal to the argument, which is this whole, oh, actually I do not need that whole thing there. X plus 4 quantity squared over 9, okay? And I know what some of you may be thinking with this. Oh, can I cancel out this 9 and this 9? No, don't do it, because this 9 is in a denominator space. So I actually need, in order to get rid of it from both sides of the equation, I will need to multiply both sides by 9, which is something I definitely want to do here. Okay, and that is a 9 right there. So on the left-hand side, we're actually going to get an 81. I'm going to go ahead and continue my work right here. So that'll be 81 equals x plus 4 quantity squared. Now we have something a lot more familiar. It looks like we're going to be dealing with a quadratic equation. So go ahead and expand out this x plus 4 quantity squared. You'll get x squared plus 8x plus 16. Subtract 81 from both sides, and you'll get 0 equals x squared plus 8x minus 65. You'll want to see if that factors. Indeed it does. Here's a little bit of work shown about how that factors. Negative 65 here. And 8 down below. So what factor pairing multiplies to negative 65 while simultaneously adds to a positive 8? That'll be a negative 5, positive 13 will do the trick. So therefore this factors to x minus 5 times x plus 13. So therefore x could equal 5, or x could equal negative 13. You want to be wary of any negative values for x. Plug that back into your original equation and say, if I put a negative 13 in this argument here, is the resulting sum, if I add just a 4 to it, going to give me a positive number? No, it will not. You'll be left with negative 9, which is not okay to feed into your log. So therefore, this solution is deemed extraneous and therefore not possible. So your only solution here is going to be x equaling 5. Okay? Very good. moving right along. We got a couple more logarithmic examples, and then I want to do several exponential equations as well. Here for number 28, you'll want to notice that we have two logarithms, same base, that are added to one another on the left-hand side of the equation. So go ahead, oops, different marker. Go ahead and throw them in the same base 2 log, but multiplied together. Okie dokie. That's what we can do. And then, oh, and if it makes you more comfortable, go ahead and put that, so it's very clear that both of those binomial factors are part of the argument there. Put some brackets around them, if you like, and go ahead and convert this into its exponential counterpart. So 2, therefore, to the third power, because the base is the base, and the log is always equal to the exponent, and the exponential is equal to the argument, which is this x plus 1 times x plus 7. Again, now we've got something super familiar again. We've got 8 equals x squared plus 8x plus 7. Subtracting 8 from both sides. Minus 1. We get something that turns out it is not factorable. Believe me, I tried. So we can always, though, rely on the quadratic formula. X equals opposite b plus or minus the square root of b squared minus 4ac. Specifically for this one, it'll be negative 8 plus or minus the square root of 8 squared minus 4 times 1 times negative 1. All over 2, which settles down to be negative 8 plus or minus, is that 64 minus 4, that's, or plus 4, excuse me, is 68. 68, well that's at least even. Turns out it is indeed divisible by 4, and the remaining factor that's left inside, so a 2 will come out because the square root of 4 is 2, and the leftover factor is going to be 17. So therefore, 4 times 17 gives us 68. 4 comes out as a 2. That's this 2 that popped out right in front here, and it's still all being divided by 2. So this 2 needs to divide both of the terms, integer terms that you see out here, the negative 8 and the 2, and in doing so, we will get negative 4 plus or minus the square root of 17. Now, plugging both of these into calculator, and by both of these I mean negative 4 plus root 17 and negative 4 minus root 17, you're going to find that one of them is going to be okay. Like this one, the negative version of it is going to be negative 8.1231 dot 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 dot. It really doesn't matter what it is because it's negative, guys, and it's so far negative that it's going to overtake, either one of these individually. So it only needs to screw up once as far as like making an argument negative. So therefore, this one is extraneous. It's a calculated result, but it's not one that we can keep because it violates the domain of the logarithmic function. So, but what about the other side? What if we took negative 4 plus the square root of 17? Well, in that case, we would get 0.1231, which is totally cool. Like we can take that, and what did we need to take it to 3 decimal places? AKA, it's also known as specifically for negative 4 plus the square root of 17. That would be like the what's it called? Why is this phrase escaping me now? I'm wasting so much time thinking about this. It is the The exact answer. The exact answer. That's what I meant to say. Okay, we got no time to lose. Let's move on to number 40. I want to definitely do this problem, which looks hopefully pretty terrifying to some of you, but fear not. Okay, this is something we're going to be able to get through together. Let's see. Very good. Let's go ahead and right. Right. Sorry, this took me a second because it looks like I technically skipped a problem that I originally had planned here, but that's fine. Okay, sorry. Less is more for this. So notice that this equation right here has 3 terms, and that one term, the leading term, is exactly, what's the word I'm looking for? Twice the degree of this term right here, where this term right here has a degree of like 1/2. You would raise it to the 1/2 power, whereas this one has a degree of 1. Whenever you see this, you can think of the equation as being quadratic in nature, and you can move forward with trying to factor it, if possible, using a u substitution. So I'm going to go ahead and do something that might not be super intuitive, but it's going to help us get through this. Let u equal the square root of the natural log. Excuse me, let me clean that up a little bit. The natural log of x. Okay, and if we do that, we can move forward with looking at this in terms of quadratic equation. And in doing so, you may notice that this is indeed factorable. So the numbers are pretty small, so hopefully we can go straight to the factored form with relative ease being u minus 2, u minus 1. So that means either u equals 2 or u equals 1. But what was u again? Well, u is the square root of the natural log of x. Either that equals 2 or the square root of the natural log of x equals 1. Okay, well, those need their own solutions to them. So in order to move forward with this, we're going to have to get this out of the square root by squaring both sides. And we're going to do this simultaneously to both equations. And that'll give us the natural log of x equaling 4. Or the natural log of x equals 1. And here, in order to get x by itself, you would need to either, you can think of raising both sides as exponents on an e, right? Or, you know, do the conversion rather. So the base is the base. The base of the natural log is e. The natural log is always equal to the exponent, and the exponential is always equal to the argument. Similarly here, e to the first power, or just e, is going to equal x. So these are actually our 2 solutions, believe it or not, to that. Okay, so those are all the logarithmic equations that I had planned for this lecture. Let's go ahead and solve some exponential functions as well. As exponential equations, rather. Okay, so I know I say function here. I'm wondering if the book has it written that way as well, because that would be an odd term to use. In any event, let's go ahead and crack it out. So whenever you have exponential expressions equal to other exponential expressions, or just seemingly like whole numbers, you're always trying to look for the common base and see if you can cancel that common base on both sides and set the exponents equal to each other. That is definitely possible here. In fact, let's go ahead and change the marker. And because that 25 can be rewritten as something base 5, right? Certainly 25 is 5 to the second power. And we can cancel out the bases and say, well then therefore negative x has to equal 2, which means x equals negative 2. Starting off real easy breezy on this one, and then they get markedly harder from there. Nothing we can't handle though. Here you'll notice we have an exponential expression with a multiplier out in front. The first thing that I'll choose to do here is to divide both sides by the multiplier out front. So I could just have the exponential on this side. And then we can, you know, use a logarithm to convert it and then see where that takes us. Okay, so that'll give us a 2 to the 3x power equals 8/5. Now I can't take that 8/5 and rewrite it as something base 2 exponential anymore. So the best thing that I can do is, you know, convert it into a logarithm. So the base is the base, right? So an exponential base 2 is going to equivalently be a log base 2, which the exponential is equal to the argument of 8/5. And then the logarithm is equal to the exponent. What's nice about this is that the variable that I'm trying to solve for is now freed up. The only thing I need to do now is divide both sides by 3. Okay, and so x is essentially solved for, and this is some number right here when I'm hovering over with my cursor, but I'm not going to be able to really type that into my calculator yet. So this warrants a little bit of a change in base in order to determine, you know, what the value will actually be, because we need to get some sort of an approximation down to 3 decimal places. Okay, so let's do a little bit more work here, focusing on the logarithm right here. So change of base, let's go for the common log. It doesn't matter, you can do common log or natural log in order to come up with the thing that you're going to type into your calculator. And this will be log of 8/5 over the log of 2, right? Big on top, little on bottom. And notice that we're dividing it by 3, so that means that the 3 factor is going to stay behind in the denominator space. So hopefully everybody is understanding how that works there. Furthermore, we can use what we know about multipliers for logs to let it be an exponent on the 2 that's in the argument. So that's even a little bit less typing for our purposes in the calculator. So we'll have common log of 8/5 over the common log of not 2, but 2 to the 3rd power, or 8. So if you type this into your calculator, you should get approximately, so I'll do a little wiggle equal sign. If you round it to the nearest thousandth, which is what we've been indicated or instructed to do, it'd be 0.226. Okay, so just to be clear, this is the exact answer, and this is the decimal approximation out to 3 places. Okay, great. Moving on. Ooh, yeah. So here's another problem, and this one's especially fun and challenging because you'll notice that it has 3 terms to it, and the degree of the leading term is exactly double of the degree of the middle term. So this one looks like it's quadratic in nature, and so yet again I'm going to do a u substitution. What's my u going to be? Well, it should be 3 to the x power here. That'll work out nicely for me. So performing this u substitution, we'll have u squared plus u minus 2 equals 0. We can factor this, right, with relative ease. So that'll give me a u plus 2 times u minus 1 equals 0. This right here will determine through the zero product principle that either u equals -2 or u equals 1. But what was u again? Go ahead and put the originally substituted value back in. 3 to the x power equals -2, or 3 to the x power equals 1. Great. Well, if we were going to try and determine what the value of x is here, we would need to do what? Convert it into a logarithm. So we would have log base 3 of -2 equals x. Ooh, do you see a problem here, guys? Yikes, bells and whistles should go off in your head. Ah, we're trying to put a negative value inside of the argument of a logarithm? No, 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 don't do it. So this gives us an impossibility, so it's just like not possible. I don't know what kind of note you want to put here. And it's because we cannot have a negative value in the argument of our logarithm. However, here, you could just use what you know about zero exponents, i.e., right, spoiler alert, x equals 0 here, in order to solve this side of the equation. So yeah, we will have a solution, and it will simply be x equals 0. That's the only viable solution that we have. Oh, I meant to this one. Great. So a little u substitution here. Okay, here is the last problem in the set, and this one's a doozy. You may be looking at it and being like, oh, this is totally an instance in which we can do a u substitution. Well, it is and it isn't. The way that I see as the proper way to move forward with this one is to recognize that this negative exponent, negative sign in the exponent right here is going to allow us to rewrite what's going on. Oh, hold on. Let me get the right pen out here. And I'm going to choose to multiply both sides of the equation by 3 to the x power. Now, why did I do that? Because this 3 to the negative x is actually in a denominator space, and that way I can just kind of, get rid of it, so to speak, okay? But you got to do it to both sides. So that'll be 14 over 3 to the x, so to speak. The 3 to the x just kind of gets put downstairs, and times 5 times 3 to the x. Now, it might not be intuitive to folks like why I would bother with doing this. Mostly it's because I want to get rid of any x's that are A, in a denominator space, and B, in a denominator space, and also locked in an exponent. It's just like double, locked away. It's going to be hard to get to it. So if there's anything I can do to cancel out that term, or that factor right there, I'm going to do it. So here is me performing the distribution here and here, and it's going to cancel down below. I will be left with 3 to the 2x power minus 14, because it cancels, equals 5 times 3 to the x power. Now, subtracting this term from both sides, you may notice that it is now appropriate to think about doing a u substitution here, okay? Minus 5 times, and resist the urge to multiply the 5 and the 3. You cannot do that because that 3 is trapped as the base of this exponential part of the factor, so it's not freed up to be multiplied by this 5 factor that's out in front. Okay, so careful there. Yes, now let's do a u substitution of 3 to the x power. That'll give me u squared minus 5u minus 14, which equals 0. All right, and this factors out pretty well for u minus 7 times u plus 2. So either u equals 7 on this end of it, or u equals negative 2 this end. But what was u again? It was 3 to the x power. So remember, when you're trying to have your exponential equal a negative number here, converting it to the logarithm, that means the argument's going to be negative. So that's going to give you an extraneous solution. No thing can come out of this. So your only bet is to look forward to what's going on here. Log base 3 of 7 equals x. Oh boy. Do we have a log base 3 button on our calculator? Probably not. So go ahead and bust out a change of base, a natural log or common log. I tend to go for the common log for no particular reason. Certainly natural log will work as well. If you type this into your calculator and press go, you'll get approximately 1.771 as your final answer. So that's your decimal approximation to 3 decimal points, and here's your exact answer. Okay, great. So those are all of the examples that I had slated for section 4.6 on logarithmic and exponential functions, exponential equations. So now we're going to switch gears over to financial models, which are exponential in nature, okay? And they have everything to do with simple interest, compound interest, continuous compounding. What else am I reading off here? Effective rate of interest, Okay, this becomes very useful for us when we are comparing um, rates of interest for various types of like savings plans and stuff like that, right? And then this one, this last collection of formulas is for if you have a present value that you want to determine based on some sort of future amount of um, income or dollars that you want to get to, right? You need to sometimes figure out how much money you need to invest to begin with. That's what these will do for you. Whereas these interest formulas, the compounding interest and the continuous compounding interest are very much related there. You'll see that they have the same basic structure except for negative exponents. These are what you want to use if you know how much you're going to invest and you want to see how much money you should expect to get out of that investment depending on how you compound. Okay, so I've left some space off to the side here, but I don't have much to say as far as adding anything to what's provided here in your textbook. It's pretty much spelled out pretty clearly as far as I can say. Every one of these yellow boxes has all of the variables defined, and it's our job just to read very carefully the scenarios that are presented with us. And here are several examples I'm going to go through with you in this section, and that's going to allow us to determine what the appropriate formula is, and just go ahead and plug and chug. There's not much to it after that. Once you figure out what formula is appropriate, it's just a matter of being able to simplify it. So using everything that we've learned recently about exponentials, or sometimes logarithms are appropriate if we need to undo some exponential stuff. The logarithms are definitely going to become relevant to us as well, even though all of these models are exponential in nature. Okay, so what else can I say before we move on? This simple interest formula is super duper duper simple. In fact, I don't even have an example in which we use this because it's just very much too simple. It gives us an idea of like the structure, I guess, basically, of some of these other formulas, but it doesn't come up, excuse me, very much when we are actually trying to answer real world questions regarding finances. If we are compounding our interest in an investment over some discrete kind of dividing of a time frame, times per year, then this structure will be appropriate for us. If the compounding is continuous, then we need to rely on this E number, this magical Euler number that was presented to us that happens to fit financial models oh so beautifully. E's come up again if you are compounding continuously versus some number of times per year n in calculating effective rate of the interest. So these are the formulas there. Basically, we just need to more or less pick the right formula given the scenario and plug in the numbers and then use our calculators appropriately according to the syntax. So, and I can answer questions for you regarding your particular machine. So we'll just tackle those as they come. Let's go ahead and just go through these examples until we are through with this section, and then also I have one more section to cover with you in which 4.8, there's a bunch more formulas being presented about exponential growth, decay, Newton's law of cooling, and a logistic model. So one of each of those. And here we go, though. Let's stick to finances. Let's find the amount that results from the investment described here. For number 12, let's say we had $700 invested at 6% compounded daily over a period of 2 years. So this means that we're going to go up to this compound interest formula right here. This is the one we're going to use, in which our A value needs to be calculated. The principal is $700, the P. The R, the rate, is a 0.07, or sorry, 0.06. It was 6% that was in the example. And if it's going to be compounded daily, how many times a year is that? 365. Over 2 years, that means that your t-value is 2, n being this 365. Okay, so here we go. A, therefore, excuse me, one last thing. Yeah, it's just an A. That's not, they don't use function notation here. Equals 700 times 1 plus 0.06 over 365 raised to the 365 times 2 power. It's supposed to be a multiplication symbol right there. Again, type that into your calculator. Be very careful. Make sure that your syntax is correct, and then press go, and you should get, rounding to the nearest hundredth, because we're talking dollars and cents here, $789.24. I know, a little anticlimactic here, but that's what I'm saying, is that there's not much to it after you decide which formula is appropriate to use. Moving on to number 14, we have now $400 invested. That's our P. So we're going to replace that where it was 700 in the previous example. It's going to be 400 now. Instead of 0.06, it's going to be 0.07 because that's the R value. But it's compounded continuously. So we need to use, over the period of 3 years, an entirely different formula. We're going to use this PERT business because that's how we compound continuously. So it'll be 400 times E, oops, E to the 0.07 times 3. Again, careful typing this in. Make sure you ask me how to use your machine if you have difficulty figuring out the syntax. And you should get, again, rounding to the nearest hundredth, $493.47. And that's all there is to that. They get more complicated as we go. Let's continue. Let's find the principal needed to get each amount. And by each, I mean, of course, just this one. We just have one example of this ilk, okay? So we're going to go ahead and use the current or present value formula, right? So we're going to be given a scenario in which we want to get $800. So that's the amount that we're looking for. What would the principal need to be? That's the question. So the amount will be $800. We'll multiply it by 1 plus the rate, which is 0.07, that's 7% as a decimal, divided by what? How many times a year is this going to be compounded if it is compounded monthly? Well, there are how many months in a year? 12. So we'll divide by 12. That's your n value. And then the exponent is going to be negative n, so negative 12 times the number of years, which happens to be 3.5, 3.5 years. Okay? Again, careful with your calculator. Make sure your syntax is correct and you don't make any errors in just typing this in, which is just rife with opportunity to make errors. And you should get $626.61. Okay? And yep, that's all there is to it. We're just really deciding which formula to use, plugging the numbers into the correct places, and very carefully using our calculators in order to find the answer there. Now we're going to find the effective rate of interest, and since we're compounding continuously, if I go back to my formulas, I know that I'm going to be using this formula right here. R sub E equals e to the R minus 1. So here we go. What's my, I just need my R value, which is 6%. So therefore, R sub E equals e to the 0.06 minus 1. And be very careful. And with typing that in, make sure that all the numbers are in the right spots, and you should get 0.06183655 4, 6, 5, dot, 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 and it goes on forever and ever without any pattern. So why am I showing you so many decimal places, or significant figures, as some folks call it, especially those who are taking chemistry? Well, I want to tell you how you're supposed to be presenting your final answer here. Now, it's a rate of interest, right? Which means it's supposed to be a percentage, okay? So what we need to do is two things. Step one is you need to convert this into a percentage by moving the decimal place over 2 spots. And then once you do that, it's customary to take 3 decimal places afterwards. So you're going to round this number, this decimal place. So you want to be checking in with the neighbor, and that's going to bump up this 3 to a 4. So therefore, your effective rate of interest is going to be, because the decimal moved right here, it's going to be 6.18, not 3, but 4, because the 6 bumped it up by 1%. Don't forget that percent symbol. Okay, so not only do we need to recognize what formula is appropriate for this effective rate of interest problem, but we also need to know how to convert what is calculated to the appropriate units. We need it as a percentage, and we need to display 3 decimal places, because that is the convention. And how would you know that convention? By reading this problem? You certainly wouldn't. So that's why I'm presenting a problem of this type, so that you know when you see other problems like this, effective rate problems, compounded continuously uses this formula, and you need to do this percentage conversion to 3 decimal places, and then you're good to go. Okay, moving on to the next problem, we're going to determine the rate that represents the better deal. So we're going to compare two different scenarios here. Oh my goodness, I think I forgot to put what it was daily. So sorry. Let me just kind of fix that there. I need to make a note of updating that in the without notes file. So number 30, add daily. Just need to mess up a note. Okay, great. So, which is going to give you the better rate? 8% compounded semi-annually, so that means twice a year, versus 7.9% but compounding it daily. So we're compounding it more often, but the rate is slightly less. Does that mean it's going to be a better deal than the 8% compounded semi-annually, or will the higher rate compounded less often going to give you the better rate? That's what we're trying to determine here. So setting up the two scenarios here, we have R sub E for this scenario is right here. That's going to be 1 plus 0.08 over 2 to the 2 power minus 1. Or we're going to have this scenario here. This other R sub E is going to be calculated as 1 plus 0.079 over 365, but raised to the 365th power minus 1. Again, carefully typing this into your calculator, you should get 0.0816, okay, for this answer. And the resulting answer here is going to be 0.08219 ... We have enough significant figures to make an adequate comparison. So which one is better? Let's say that this rate is going to be something that you want to be higher, like, right? If it's a interest rate on the low, obviously you want that to be lower. But we want to know which one is higher. Well, it's definitely this one here. It's a slightly larger number. So that means 7.9% compounded daily is going to be the better deal. Okay, So we'll just kind of box that up as our final answer, and we're good. Oh, I went ahead and drew over the next problem there, but that's okay. I think we'll be able to read it just fine. So this one is trying to determine the time required to reach a goal. We want to know how many years will it take for an initial investment that says 25,000 to grow to 80,000. Assume an interest rate of 7% compounded continuously. So the continuously bit tells us which formula we're going to use. We're going to use the PERT formula, and we know how much it's supposed to end up being. That'll be the 80,000. So that's the amount, and the principal was 25,000, right? And that'll be multiplied by e to the r, 7%, 0.07. The t is going to be the unknown. So notice that our unknown value is stuck in an exponent on an exponential expression. So we're going to have to rely on some logarithm in order to free up that t variable and find its value. Let's first start by dividing both sides by 25,000. That's going to be the first step in getting at that t solution. Okay, obviously those cancel, and this is going to reduce down to 3.2. Okay, 0.7t. Great. Now we're in a position to convert this into a natural logarithm. Why a natural logarithm? Because it's currently an exponential equation with base e. So the base is the base. So I want a logarithm base e, which is having an argument of 3.2. Excuse me, I put 3.3 on accident. Let me correct that. 3.2. And that's supposed to be equal to the exponent, which is 0.07t. Simply divide both sides by 0.07, and you will be able to find the value of t. So there we go. Click that into your calculator, and you will get that t is approximately 16.616440, blah, 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 blah. We're going to round it to the nearest hundredth, okay? Now, how would you know about that convention? You probably wouldn't. Rounding it to the nearest whole year is kind of a little bit weird. Usually we round it at least to the 10th place. Here I'm going to choose to round it to the nearest hundredth. So it'll be about 16.62 years are needed in order to have that initial $25,000 investment grow to an $80,000 investment. Okay, so that'll be everything that we're going to cover for 4.7. Now 4.8 is more exponential models, but those are going to be concerning growth and decay, cooling, according to Newton's law, and a logistic model, which is basically a fancy way of saying a population model. Okay, so notice that these growth and decay models are pretty much, they are the same structure exactly. We have an initial value, n sub naught or a sub naught, depending if you're talking about growth or decay respectively. We have e to the kt factors as well. K is going to be positive if we're talking about growth, and K is going to be negative when we're talking about decay. That's pretty much it as far as the difference between these two models. They are the same model, it's just we have different letters indicating whether we're talking about growth or decay, and we know something definitively to be true about the value of K. That has to be positive for growth or negative for decay. Newton's law of cooling, I could not tell you how that's derived. If you wanted to spend some extra time looking into how that was structured, like how that came about, that's a physics endeavor. It's a little bit outside of my scope. What we want to focus on for our purposes today is just being able to use the formula in order to answer a specific question involving the cooling of an object over time. And then lastly, the logistic model is going to be advantageous for us to be able to determine some organism's population after a certain amount of time. So notice the various letters that they use here. A, B, and C are constants. A and C both have to be positive, and B is going to be positive if we are exhibiting growth for our population, or if our population is dwindling in size. If we're losing members over time, then your B value is going to be negative. So basically, a B is the growth factor, the growth rate, and C is going to be your initial value. We'll get into this logistic model and all of the components in it when we tackle the examples associated with them. So I have one of each. Okay, so for number 6, this is going to be our growth model. Okay, so we're going to basically be using a model just like this, one that we have to create. Okay, now oftentimes with these examples you'll be given the model that you're going to use, but sometimes you won't be, and it'll be your job to know this formula right here. I mean, it's the same structure where they're talking about growth versus decay, so it's really only memorizing one formula. You just have to know that the K value, the growth rate, is positive for growth, negative for decay. Okay? So for number 6, for bacterial growth, it says a culture of bacteria obeys the laws of uninhibited growth. Okay? So for part A, they're like, if N is the number of bacteria in a culture and T is the time in hours, express N as a function of T. Okay, no sweat. We know this formula. This is going to be N of T is equal to N naught, which is our initial population of bacteria, multiplied by E to the KT, where K is our growth rate, and it's going to be some positive number. If 500 bacteria are present, I'm on part B now, initially, and there are 800 after 1 hour, how many will be present in the culture after 5 hours? Ooh, this is a multi-part problem right here. We're going to start things off by saying that we know that N of T, the population after 1 hour, is going to be 800, because that initial population was 500. We know N sub naught is 500, and then it'll be multiplied by E to the well, we don't know what the growth rate is, but we know the amount of time that has gone by, 1 hour. 1 hour, so times 1, which is just going to be an exponent of K. Great. So this scenario needs to be entertained in order to calculate the value of K, aka the growth rate. So in order to do that, we're going to divide both sides by 500 to start off. We want to get K by itself. So that turns this into 1.6 e to the K power. So now we can think of it as converting into a natural log, if you like. So the natural log of 1.6 therefore will equal K. Use that calculator, and therefore K is going to be approximately 0.47. So that's the growth rate. We have a 47% growth rate. Okay, so that's part B. Let me go ahead and box my answers so far. Here's A, here's B. The first part of B anyway. Oh, actually that's not answering B. I am so sorry. This is something we're going to need in order to answer the thing in part B. It's only part of the story here. Now that we have K, we can plug that into the formula, right? And we can determine how many bacteria there will be after 5 hours. So when T equals 5, okay? So let's go ahead and we'll put that down here. N of 5, so to speak, will be 500 e to the 0.47 times 5, because remember the T value here in the scenario is 5. Okay, so carefully type that into your calculator, and what shall you get? You will get 5,242.784,862 ... But we're talking about bacteria, right? So how many bacteria do we have? We need to present our answer in numbers of whole bacteria, so round to the nearest whole number. So the 7 here is going to bump this 2 in the ones place up to a 3, so that'll be 5,243 bacteria. There we go. That's how many bacteria are present after 5 hours. Cool. So that's B. Here's A, B. Let's go ahead and tackle part C. It says, how long is it until there are 20,000 bacteria? Okay. 20,000 is what we're looking for. We know that we are initializing the population with 500. We know the growth rate, 0.47. We don't know the amount of time. That's what's being asked. How long until we get to 20,000 bacteria? So start off by dividing both sides by 500. Oops, 500, not 5,000. My bad, get rid of that. Okie dokie, and boop boop. We're going to have this equals, what, 40? Okay, so that'll be 40 equals e to the 0.47t, or 7t. So we're going to take the natural log of both sides. It's one way that you can think of it. And then we'll have to divide both sides by that 0.47. So natural log of 40 divided by 0.47 will give you your t value, which is approximately 7.85. Okay, so you get some long number, but rounding it to the nearest hundredth is customary for units of time. And the units here specifically are hours. Okay, great. Whew, so that was part C. Moving on. So that's 1 down, 3 more to go, and then we're done with this lecture. Sorry, it's a bit of a long one. That's what happens sometimes when you have a lot of applications you need to cover. Okay, so moving on to number 10. We are dealing with radioactive decay, and we're going to introduce this idea of half-life. So half-life is something that comes up a lot when you're talking about carbon dating or dealing with radioactive materials. We want to know when half of it is still present, okay? So the way that you will deal with this is recognizing that we need a decay model, right? So what's the decay model again? Well, it is A of t equal to A sub naught e to the kt, right? But if you are dealing with half-life, that's going to be, you want half of what was originally there, so the initial condition is equal to that formula. And then what happens if you recognize that you cancel out your A sub naughts? Then essentially the half-life formula therefore becomes 1/2 equals e to the kt. Okay, you don't even need to know how much is initially there in order to find the half-life. You just need, you just need the number of years in order to find the rate, that is, okay, which is actually what exactly we need in order to find how many grams will be present after 100 years and 1,000 years. So, just to be clear, let me read the prompt from the beginning. The half-life of radioactive potassium is 1.3 billion years. What is 1.3 billion years? Look at it as a standard number. Well, here's 1,300. There's 1,300,000. Here's what 1.3 billion looks like. 1,300,000,000. That's quite a big number. So this is the half-life. So this is the t that we're going to be using in order to calculate our growth rate, okay? And we're talking decay here, so we should have our growth rate come out to be a negative number. And that's exactly what's going to happen. So let me go ahead and use this formula right here and say, all right, halfway through e to the, so that's 1 billion 300 million times t, and we're going to need to excuse me. Yeah, so if we settle this down and have it solved for t, it'll look like the following. The natural log of 1/2 divided by 1.3 billion. Type that into your calculator, and you're going to get the following. Okay, this is k, and therefore k equals negative 5.3319014 e to the negative 10 power. So that's this number times 10 to the negative 10 power. So we're essentially moving this decimal place over 10 spots to the left. It's going to be a super duper duper small number, and it's negative at that. Okay, so this is what we should expect, because it takes 1.3 billion years just to get rid of half of radioactive potassium. Okay, just to get rid of half of it, it takes literally 1.3 billion years. Wow, that's a long time. So if we want to know how much is going to be left after only 100 years or 1,000 years, spoiler alert, we shouldn't expect to be having very much of it disappear after that relatively small amount of time. So keeping into account this k value, I'm going to actually box that up in this magenta color, because I'm still going to use k as a variable. I'm not going to rewrite this number down every single time. But I am going to give you a to the 100 year scenario is going to look like this. Well, there was 10 grams to begin with. That's our a sub naught, a sub 0, e to the k, which is just this. I'm just going to point to it, times 100. So very carefully type this into your calculator, and you should get, oh, it's so silly, 9 watch this, 6 nines, 467 grams. LOL. So barely a tiny little blip of a gram is removed from the radioactive potassium after 100 years. How much is left after 1,000 years? Well, this formula right here will give you the answer. Remember, k again is going to be this ridiculously small but many-digited number, and this will give you, if you're careful about typing into your calculator, it'll be only 5 nines this time, so a little bit less, 4668 grams. So even after 1,000 years, the thing that we're supposed to glean from this is that it takes a really long time for radioactive potassium to decay. So after only 100 years or 1,000 years, tiny little infinitesimally small amount is being released because this particular material has such a long half-life. Okay, so hopefully that makes sense to us. We feel good about it. All right, 2 more examples, and then we are done with the lecture. Thank you so much for your attention. I know it's a lot. Let's entertain this Newton's law of cooling problem, in which a thermometer reading 72 degrees Fahrenheit is placed in a refrigerator where the temperature is a constant 38 degrees Fahrenheit. A, if the thermometer reads 60 degrees Fahrenheit after 2 minutes, what will it read after 7 minutes? Well, we need to take the right formula, which is going to be Newton's law of cooling, and here it is. It's U, oops, use the right utensil, U of T. And we have lowercase t's and uppercase t's, so careful, okay? Because case matters for formulas. Where uppercase T is going to be the constant temperature in the environment, lowercase t is going to be the amount of time, and U of T is going to be the temperature after a certain amount of time for the heated object, and U sub naught, which I have right here, is going to be the initial temperature of the heated object. Okay? And K is the rate at which the item is cooling. Okay, so here's the formula that we're going to use. And for part A, let's go ahead and plug and chug, y'all. So we know that 60 degrees Fahrenheit is going to be the resulting temperature after a certain amount of time. So that's your U of T, 60. The temperature in the surrounding area is 38 degrees, so that's your capital T. And the initial heated temperature was 72 degrees. So 72 goes for the U sub naught minus 38 degrees, which again was the surrounding temperature. And we have e to the, we don't know the value of k, that's exactly what we're trying to calculate here, the rate of cooling. And we know that it's going to be 2 minutes time. That's going to be our scenario here that we're entertaining for part A. So we have 38 that we're going to subtract from both sides, and we're going to simultaneously perform this subtraction, which is going to leave us with 22. That's 60 minus 38 is equal to 72 minus 38 is 34. E to the 2k, let's say. So k times 2 just became 2k here. We're going to divide both sides by 34 and reduce that fraction and get 11 over 17. I know, kind of weird, but it's nice to work with the smallest numbers possible. Okay, just to be clear, I divided both sides by 34, so 22 over 34 reduced to 11 over 17. Hopefully everybody's on board with that. Equals 2 to the k. Or excuse me, e to the 2k power. Now we're ready to take the natural log of both sides, or to convert it into the natural log, however you like to think about it. And that'll give you 2k over here, so we can just divide both sides by 2 in order to get k all the way by itself. Hopefully everybody's okay with the extra steps that I'm kind of skipping here. And that way we'll get a k of negative 0.2176590,356. This is the extent of the digits that my calculator would give me. And you know what? In order to avoid round off error, it's best to use as many digits of along the way calculations that you need to take in order to answer a certain question. So we just calculated k. Great, that doesn't answer our question. What we wanted to find was what will it read after 7 minutes. So now we have to go back to the original function for part A, and let's go ahead and just directly under here we'll get, we're trying to find u of 7, and that's going to be 38 plus 72 minus 38 e to the t times k. And again, I did calculate my k value, but I'm not going to rewrite the whole thing again, so I'll just point to it if that's okay with everybody. And let's go ahead and just press go on our calculator, and we will get, rounded to the nearest hundredth, which is the convention, 45.41 degrees Fahrenheit. So that is the temperature after 7 minutes in the fridge, okay? Cool. So now part B, how long will it take before the temperature reads 39 degrees Fahrenheit? So we're going to take that same formula and to set it equal to 39 this time. 38 plus 72 minus 38, which you don't have to necessarily rewrite this every single time. We know the difference is what, 34, so you can write that if you want to in that place. So t again times k, which we have calculated. I'm going to just point to it and say that's the value of k, is this big old number. Furthermore, let's see, we would subtract 38 on both sides and get a 1, and then divide by 34. So hopefully everyone's comfortable with me saying in the next step we got 1 over 34 is equal to e to the tk value, remembering that k is this already calculated value. Then we take the natural log of both sides and divide both sides by k. And that'll give us our t value, which if you plug this into your calculator, remember, k is this number right here that we already calculated. There's no reason to keep writing it so many times in order to make our point. So let's round to the nearest hundredth here for this time, this amount of time, and it'll be about 16.20. And so since there's a 0 in the hundredths place when you round it, we could just call it 16.2 minutes. I know it's a little anticlimactic. Once we get everything set up, we just say, and then push the buttons. But that's kind of the nature of this work, is that the hardest part about it is the setup. And once you get the setup going, well, then you get the benefit of relying on your calculating machine in order to continue. And hopefully that feels kind of nice. It doesn't feel like a cheap shot, okay? Here we go. So let's continue. We need to answer part C here, which is to determine the time that must elapse before the thermometer reads 45 degrees Fahrenheit. So that'll look like this. Now we gotta have 45 equal to 38 plus 72 minus 38, blah, 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 e to the tk. Remember, we're using the same k value there. Nothing has changed in that regard. Subtract, divide by 34, and you'll get, 7 over 34. And also, so that equals e to the kt. We're going to take the natural log of both sides and divide by k. Wow, ran out of room. So ever so much there. Okay, so then that gives us a value of what? About 7.26 minutes. Okay, and that's that. Just careful typing into the calculator at that point, and you'll get the answer that you seek. Lastly, let's go ahead and answer part D, which is more of a qualitative question more than anything else. It asks, what do you notice about the temperature as time passes? Well, it's definitely decreasing, as would be so very obvious, because, you know, we're talking about cooling. So yes, temperature decreases. What does it seem to be decreasing to? Well, it's going to eventually decrease all the way to the ambient temperature in the room, which is 38 degrees Fahrenheit. Okay, 38 degrees. I didn't mean to put 30 right there. Here we go. So it's like approaching that ultimate degree measurement, okay? Cool. Whew, almost there, guys. Let's entertain one population logistic model, and it's all about eagles, bald eagles. Isn't that a beautiful, majestic beast? Okay, often environmentalists, it says, capture an endangered species and transport the species to a controlled environment where the species can produce offspring and regenerate its population. Oh my gosh, the story with the California condors in regard to that, their population regeneration has been like really super cool. You guys should read up about condors. Way more interesting than bald eagles, in my opinion. And I'll have you guys know that on a recent car trip, I saw a condor fly overhead while I was driving through Gorman on the Grapevine, and it was life-changing. Oh my God. Okay, enough about that though. Let's get through this problem together. We are given the scenario in which we suppose that 6 American bald eagles are captured, transported to Montana, and set free. Based on experience, the environmentalists expect the population to grow according to the model. P of t equals 500 over 1 plus 82.33 e to the negative 0.162 t, where t is measured in years. Okay, so how did they come up with that? Don't worry about it. They're giving you the population logistic model, so it's just our job to be able to use it and to also identify certain components, which is exactly what we're going to do in this initial bit, okay? So A, this is what we're doing in order to determine the carrying capacity of the environment. So how many bald eagles can we expect to hold in this particular environment? Well, that's going to be this value up top right here, okay? So that'll be, oh goodness, what's going on here? Hold on just a second. Thank goodness I was able to recover this document. Because everything froze up on me. Okay, let's go ahead and punch this out real quick. So part A, determine the carrying capacity of the environment. Look at this, guys. It is the numerator value in this particular function. Okay, so part A, this is going to be 500 eagles. That's how many eagles the particular environment can handle. Okay, that's what is meant by carrying capacity. Part B. What is the growth rate of the bald eagle? Well, that'll be this little number right here. Okay, I'm going to underline it here. But since it's in a denominator space with a negative exponent, it's actually a positive, it's a growth rate. Okay, so just take off the negative sign and take that number and turn it into a percentage. So 16.2% is the growth rate. Okay, part C. What is the population after 3 years? Well, that's precisely what this function models. So let's take it, P, and plug in 3. So the way it'll look is you'll have 500 on top. Just copy everything down carefully and accurately. Put that into your calculator with the correct syntax, with a t value of 3 here, okay? And when you do that and you press equals, you'll get 9.68247, blah, 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 blah. But remember, we're talking about eagles, so we need to round this to the nearest whole number, so you'll say about 10 eagles. That's how many eagles you should expect in this population, given the model after 3 years. Okay. When will the population be 300 eagles? Well, we need to set our population logistic model, in this case, equal to 300, and solve for t, because they're asking when. When? I don't know. At what t will we have this happening? Okay, so this is where it can get a little bit dicey algebraically, but I'm here for you. Okay, so what do we do first? Well, you'll want to recognize that the t that you're trying to solve for is in an exponent, and it's in a denominator space, so it's kind of a double whammy as far as being hidden. First thing we want to do is put this 300 over a 1 and then flip over both sides of the equation. Believe it or not, this is what you want to do. So that'll have you 1 over 300 on one side, and then 1 plus 82.33 e to the negative 0.162 t all over 500. Now you can multiply both sides by 500 and then also reduce the fraction. So it's like, here, let me see. I'll put some notes in this regard, but I kind of want to, right? And then those zeros will cancel out, these 500s will cancel out, and we'll be left with 5/3 equals 1 plus 82.33 e to the negative 0.162 t. We'll subtract 1 from both sides, and we'll get 2/3 equals 82.33 e to the negative 0.162 t. Okay, and what next? We've got to divide both sides by 82.33, which is, right, so we got to, basically it's multiplying the 82.33 times this 3 down here, so it's like 2 over 246.99 fun equals e to the negative 0.162 t. We're so close. Now we're ready to take the natural log of both sides, and then we're going to divide both sides also by the negative 0.162, the way we've been doing for previous examples as well. So this is therefore going to be what you plug into your calculator. Natural log of this whole thing divided by negative 0.162. Ever so carefully type that into your calculator, and what do you get? T is about 29.7. Why are we rounding to the nearest tenth instead of the hundredth like we did before? I'm not really sure, to be quite honest. This is just what the back of the book says, but this is based off of a decimal that could be approximated if you want to do it to the hundredths place. It'd be 29.73 years. I don't know. Doesn't matter. You could do to the 10th, and that would be fine. So that's how, basically almost 30 years is how much it's going to take in order for us to get 300 equals in this particular location. Okay, last part of the last question. We're almost done, guys. Thank you for your attention so very much. We want to ask, how long does it take for the population to reach 1/2 of the carrying capacity? Well, the carrying capacity was how much again? It was 500. So half of the carrying capacity would be 250. So if we set this equal to 250, oops, hold on, equals this 500, this, plus 1.82.33 e to the negative 0.162 t. Oh man, my kids are really just about to explode. Okay, so what do we want to do here? We want to finagle this in the same exact way that we did here, but maybe avoid some of this, showing so many steps here. So I'm going to go ahead and say dot, dot, dot. You'll find that this equals 1/82.33, equaling e to the negative 0.162 t. All right, and then that'll be the natural log of 1/82.33 all over the negative 0.162. That'll give you your t in this other scenario where we're half the carrying capacity. Well, that'll be at about 27.23 years. Whew. So that's that. Goodness gracious. So if you're trying to get to half the carrying capacity or 300, it's like there's not much of a time difference going on there, just about 2 years, a little bit more than 2 years. Cool. So that's an overview of some of the different models that we can expect given exponential formats. Let's definitely continue this discussion in class the next time that we meet. Thank you so much for your attention. See you soon.